Okay, so we begin the buck converter discussion with this lecture. If we look at modern systems on chip, which is basically single integrated circuits on which entire electronic systems are integrated, if you look at a small SoC, they'll have three major parts inside the chip. So this is a chip. Then the majority of the chip is a digital core, which is a large digital circuit. It will have processor and memory and control and all kinds of things. There is usually a small analog module, and then there is another module called input output, which communicates with the outside world. So signals coming from outside the chip and going back out of the chip. And it turns out that each of these modules requires a different DC voltage to operate it. These are typical numbers. So if the supply is 3 volts, then the digital core may work at 1.2 volts. The analog circuits may work at 2.5 volts, and the input output circuitry may work at 1.5 volts. I say may because in fact so that's why I say small. Elaborate system on chip, the digital core itself will have different modules that work at different voltages, and analog also may have two different, and so on. But this is the simplest possible case. Now the chip itself is supplied from the outside by a single voltage. This may be a battery. For example, if you think of your smartphone, the smartphone works off a single battery that is connected to it, and inside the smartphone, this I'm taking the example for 3 volt, whatever this voltage is, has to be converted to different DC voltages as needed by different parts of the chip or the system. In fact, the smartphone will have not only one SoC but other components and devices also. So one has to convert this 3 volt to, in our case, at least 3 different DC voltages, 1.2, 2.5 and 1.5 volts. This is done by a circuit called a DC to DC converter. And so in fact there are, I say converters because there are actually 3 DC to DC converters inside this block, each converter converting from 3 volts to individual voltages. So there will be 3 converters inside this for each of these voltages. So what we are going to do over the next few lectures is discuss the basic design of a DC to DC converter, which is basically an electronic circuit. Alright, so let us start with the very basics. So let us say that we want to have a circuit that converts a 3 volts at the input to a 1.5 volt at the output, and that whatever this module is can be represented by its Thevenin's equivalent resistance, which we call RL, L for load. And we ask ourselves a question, well, what circuit can we use here to convert a 3 volt to a 1.5 volt given the value of RL, right? So this is a voltage smaller than this. So we say, well, the simplest thing we can do is we can just do a resistance division. Assuming, let us say, RL is 10 ohms. So we connect a resistance in series. So now we have an R1 in series with RL, and so this is a voltage divider. And of course, if this is 1.5 and this is 3, then we make R1 equal to RL, then both the output voltage will be 1.5 volts. So this is a simplest DC to DC converter, and these are the equations. So we get R1 equal to 10 ohms. Now let us look at the efficiency of this circuit, because that becomes an important thing. So the first thing we say, well, let's find the current in the circuit. So the current is 3 volts divided by 10 ohms plus 10 ohms. So 3 by 20, that is 0.15 amperes. the power consumed by RL is I squared RL, which is 0.0225 times 10, so 0.225 watts. The power consumed by R1 is of course the same because RL and R1 are equal, so that also consumes 0.225 volts. Therefore, the efficiency of this DC to DC converter, where efficiency is defined as the power consumed by this circuit divided by the power supplied by the 3 volt source. So the power consumed is 0.225 watts and the power supplied is 0.225 plus 0.225, and so that is of course a 50% efficiency. So in other words, what we are saying is that 50% of the power is lost by the DC to DC converter circuit. So our goal is to operate this module here or this chip here, and in order to operate or supply power to this chip, we are wasting 50% of power from whatever is supplied. This is of course a very high fraction of power that is wasted, and it in most SOC applications, particularly battery operated systems, this kind of efficiency is not good enough. We don't want to waste 50% of power because the battery will drain that much quicker. So we want to look for ways therefore that will reduce this power consumption by the DC to DC converter itself, so that a majority of the power supplied by the 3 volt source actually reaches the chip or the system that we are trying to drive. Okay, now a little on the side, and then we'll come back to the question of efficiency. Typically, the load resistance RL is variable, and that is, let's go back to the, so the reason this is so is because, let us talk about the digital core. So this is a digital core, of course is an extremely large system. It will have millions and millions of transistors and many modules. And what is done to save power of this digital core is that what happens is, in actual operation, not all the subsystems inside this digital core are being used. At some point in time, one subsystem is used and many others are just lying idle. At another point in time, another subsystem is used and some others are lying idle. So what is done is, this is called intelligent power management, is that whenever subsystems are not being used, they are either switched off or they go into a standby mode so that they consume zero or very little power. And when they go into standby mode, so what happens is, because of this, the power drawn by the digital core varies as a function of time, depending on which subsystem is being used. And if the power drawn is varying for a given voltage, what that means is that the Thevenin's resistance of that subsystem is varying as a function of time. Alright, so because that will that will model the power being drawn by the subsystem to vary as a function of time. So let us go back here. So what happens is, therefore RL varies, but as RL varies, we don't want the supply voltage to vary. We want the supply voltage to remain constant, 1.5 volts, because whatever subsystems are being used, they must get a voltage of 1.5 volts. Now, maintaining the DC supply voltage constant as RL varies is called as load regulation. This process of maintaining it constant is called load regulation, regulating the voltage as a function of load variation. Load regulation is achieved by a negative feedback loop. Now we'll see this a little later, after two or maybe one or two lectures. Right now we'll focus on increasing the efficiency of the DC to DC conversion. So of course, now let us go back here. So here if RL varies, of course you can see that if RL varies and R1 is of course a constant, then this voltage 1.5 volt will also vary, and that is what, so we'll put a negative feedback loop to control this voltage, to maintain this voltage constant as RL varies. And as I said, we'll come back to this after a while. Let us now discuss how to increase the efficiency of this DC to DC conversion. Now this actually is a fundamental limitation, right? So if I have whatever I put inside this DC to DC converter block, if this circuit is a DC circuit, then if I want this voltage to be 1.5 volts and if this voltage is 3 volts, then there has to be a 1.5 volt across this DC to DC converter circuit here, and a current is flowing which is equal to 1.5 volts divided by RL. That current has to flow here. Whatever we put, either we put R1 or whatever else we may think of putting, there will be a voltage drop across that circuit and there will be a current in that circuit, and that current will be 1.5 volt by RL. Therefore, there is necessarily a large power consumption by the DC to DC converter, and so the efficiency of this circuit is fundamentally limited. It can never become very high because of this fundamental limitation. So given this, then what can we do to put something here that still consumes as little power as possible and still provides an output voltage that is 1.5 volt when the input voltage is 3 volts? That is the question. So the answer is actually very counterintuitive. So let us look at the answer. The answer is we put a switched circuit and we put an inductor. So let's see what happens. So S1 and S2 in this circuit are turned on alternately, so that when S1 is on, this V1 is 3 volts, and then when S1 is off and S2 is on, V1 is 0 volts. So the voltage at V1 alternates between 3 volts and 0 volts, and that, it turns out, as we'll see in some detail in the following slides, causes this voltage to be almost equal to 1.5 volts. And now if we assume switches to be ideal, so that they don't have any resistance, and we know that the inductor does not consume any power, it absorbs energy, it gives the energy back to the circuit, and so now this DC to DC converter block consumes no energy. It is theoretically at least ideal and has no power consumption at all. But this is, as I said, this is counterintuitive. How can such a circuit give a DC output, right? So let us think about this. How can such a circuit give a DC output? Let us see. Okay, so instead of putting switches, just for the sake of understanding this circuit, what we'll do is we'll connect a voltage source here whose value is alternating between 3 volts and 0 volts. So our circuit is a voltage source, an inductor and a resistor. So this is our circuit, an inductor, resistor and a voltage source which will make alternate between 0 volts and 3 volts with some period. So let us say the period, so this is a square wave, and let's say the period of the square wave is capital T and the voltage is 3 volts for a time capital T1. Alright, now let us put some values to get a better sense of this, the behavior of this circuit. So let's make RL equal to 10 ohms and let's make L equal to 100 microhenries, which is a reasonable realistic inductance value. So the time constant of this circuit, L by R, this is a simple L by R RL circuit, so it has a time constant L by RL. I'm sorry, this is RL, so that is 100 micro by 10 ohms, so that is 10 microseconds. Alright, Now let us think about what happens to the output voltage, the voltage across RL we'll call the output voltage. What will VO look like if this capital T, the time period is 200 microseconds, and capital T1 is half of 200, so 100 microseconds. Or in other words, if these times are 10 times the time constant of the circuit. Alright, so let's say initially the voltage is 0, suddenly it goes up to 3. It stays at 3. So when this is 3, this is an RL circuit. So we know from last semester that the behavior of the voltages and currents will be exponential. So VO will vary exponentially and it will rise from 0 to 3 volts. Alright, with a time constant of 10 microseconds. So this is what the plot will look like. So if you assume that initially the voltage is 0, then it will go to, I'm sorry, this is 5 volts. Okay, let's make this change. I kept changing this back and forth. So yeah, so let's make this 5 volts, doesn't change anything else. So the output voltage varies between 0 and 5 volts. It goes up to 5, nearly 5. Then when the input goes to 0, the output goes back to 0 exponentially and keeps going back and forth between 0 and 5 volts. This is what the output would do. Now, I note for future reference that the average output voltage is 2.5 volts. Between 5 and 0, the average is 2.5 volts. Alright. Now let us ask ourselves a question. What happens if we reduce capital T? Right now we made it 200 microseconds. And let us make T1 as T by 2, which is 100 microseconds. So we'll keep capital T1 fixed as capital T by 2. And let us vary capital T and see what happens. So what happens is capital T is reduced. Alright. In fact, you may want to pause and think about it before proceeding further, but I'll proceed further here. So what we'll do is let us look at some SPICE just to find quick answers. We'll do SPICE simulations. So this is our circuit. We have a voltage source whose period is 200 microseconds, and the duty is basically capital T1 by capital T, which we keep fixed at 0.5, and so we'll apply a pulse, and the resistance is 10 ohms and the inductance is 100 micro as we have designed, and the time constant is 10 microseconds. So let us find the output voltage for this as we already saw in that plot. So this is what we get. All right. So the output goes to 5 volts and then to 0 volts and 5 volts and 0 volts. What did I show the output? No. Okay. Fine. So all right. Now let us reduce the cap period. So let us make it 100 micro. Keep it half. All right. So now, in fact, let me plot the. Okay, why not? For now, let me plot it. We'll see afterwards. Okay, so this is the input. So the input is a square wave. The output takes time to reach the input and so on. Now let's make the time period half. So 100 micro. So let's see what happens. All right, what happened? The output is charging to slightly less than 5 volts because now the time constant is only so this is 50 microseconds, so we are allowing it to charge only for 5 time constants, and so it is charging to slightly less than 5 volts, and this is discharging to slightly less than 0 volts. Alright, it's a little more complicated, but I'm not describing that because we'll see as we go along. So let's make it 50 microseconds. All right, halve it further and let's see what happens. Alright, so what's happening now? Now we are charging it only for how much? 25 microseconds. The time constant is 10. So what is happening is this charging starts at 0 and it reaches about, let's say, 4.6 volts, and then we are making the input voltage goes back to 0. So the output starts discharging. No, I'm sorry, discharging is the wrong word, but decaying. But it doesn't reach 0 because we are not allowing it to decay all the way to 0. It's reaching some minus 0.5 or 0.4 volts. Then again it goes up, goes down, goes up, goes down. Alright, so this is what happens. Now let's make it 10 microseconds. Alright, and let's see what happens. Alright, so now the input is going up to only about 2 volts and then it is going down. It reaches only here, and the next time the input goes high, the output goes up higher. When input goes low, the output goes lower, but not to the same voltage, and it keeps doing that. Now let us increase the time of this simulation. This is 30 micro. Let us make it 100 micro. Okay. All right. So this is interesting. So the output starts here, goes down, goes up, goes down, goes up, goes down. And the highest value it reaches is increasing, but now it has settled down. In here, this value is remaining constant, this value is also remaining constant. Alright, let us study this in some detail. So I'm going to close this one and let us study this. Okay, so this is the plot. Again, I have plotted it for only 80 microseconds instead of 100 because the output had already settled down by 80 microseconds. Now I am defining two terms. So when the input is 5 volts, the output, let's say in the second cycle, is going from here to here. So I am calling this delta VR, R for rise. So this is the change in the output voltage during the rising period, and then this is the change in the output voltage during the falling cycle. All right, and eventually the voltage is oscillating between 3.1 volts and 1.9 volts. Alright, now what I have done here is made a table of the cycle. So this is the first cycle, this is the second cycle, this is the third cycle. Alright, so for each cycle I have actually measured and tabulated the values of delta VR and delta VF, the rising voltage and the falling voltage. So what we see in fact here is that the rising voltage is the magnitude is highest in the first cycle. Alright, we can see here 1.96 volts in the first cycle. The magnitude of the falling voltage is 0.76 volts. And as we go through successive cycles, delta VR we see is decreasing, alright, from 1.96 to 1.20. At the same time, delta VF, as we go through successive cycles, is increasing from 0.76 to 1 to 1.1 and so on. So one is decreasing, one is increasing. Initially the rising one is high, the falling one is low. Therefore at some point the rising and the falling will become equal, and when they become equal, the output voltage will oscillate between the same two output values, the same two high and low values, in this specific case 3.1 volt and 1.9 volt. Now this is a property of exponential charging and discharging. Alright, if you are interested, you can sit and go through the mathematics of this these cycles one after the other, and mathematically you can convince yourself that this happens independent of the value of R, the value of L, the value of the input voltage, the value of capital T. It doesn't matter whatever values one uses, it is a property that eventually such a system will settle down to oscillating between two constant voltages. All right, so this is one this is what is being utilized in this DC to DC converter. All right, why did I not make this full screen? Okay, so 1 second. All right, so again the average of these two values, 3.1 volt and 1.9 volt, is 2.5 volts, which is the same as the average of 5 volts and 0 volts, which was the case for capital T being much larger than the time constant. All right, that is one thing we observe. The other thing we observe is that the okay, let's go back. The delta VR here, the rising voltage is 5 volts. The falling voltage is also 5 volts, where for a capital T of 200 microseconds. The delta VR here has become from 5 volts 1.2 volts. All right. So as capital T is decreased, the delta V decreases. All right. It has become 1.2 volts from 5 volts. So then we ask ourselves, well, what if I keep on decreasing T further and further? All right. Okay, I didn't want to show this. So let us do some more spice. So we'll look at that same circuit and we'll reduce T further. All right. So I have, let me see, I want to start with 10 microseconds and a period of time of 10 times. All right. And let us see. And we plot the output. So this we just saw. So this we just saw. Now let us reduce the period from 10 micro to 2 micro. All right, and see what happens. Okay, so what happened? This is still increasing. It has not reached steady state of that oscillating between the same two values. So let us increase the time period of simulation. All right, so now it is eventually settled down between two values. The two values are about 2.6 volts and 2.4 volts. So the difference is 0.2 volts, 2.6 to 2.4. The delta is 0.2 volts. It was 1.2 earlier, right, when this was 10 microseconds. So now it has become 0.2 volts. Now let us reduce this further. Let's make this 0.2 and see. Okay, so now we can see, of course, that because we are not giving the output voltage time to go up and down, the steps are very small. There's small changes while increasing and decreasing. Again, this has not settled down. So now let's increase this period to the time of simulation. All right. So now it has gone up and now it has settled down here. The average is 2.45 volts still. Okay, let us reduce this further, and I'm going to skip a step and I'll make this 5000 and see. Okay, so what do we see? What we see is that when the period is made very small, the output voltage eventually is basically 2.5 volts, and it basically looks like a DC voltage. So we have been able to obtain basically a DC voltage by switching an inductor back and forth between 0 and 5 volts. Of course, I say basically because this is actually not a DC, right? So let us see. If we expand this, you can see that this is not a DC. It has a variation. Only the variation is very small, right? So look at the variation. This is 2.5011 and 2.4987. right? Practically 2.5 volt DC with a slight variation, which is called a ripple. You've come across ripple before in diode circuits also, but that was a different ripple. That was due to rectifiers. So here the ripple is about 24 millivolts, and it turns out that for applications of these SOCs, a practically DC voltage with a small ripple is acceptable as a voltage that is input to the digital circuits inside the chip, digital or analog or whatever. All right, so now we have been able to generate a DC voltage out of by switching an inductor. All right, so this is the fundamental principle of switched mode DC to DC converters. All right, so this is what it is. Okay, so this is what we just saw, and so this is the basic buck converter. Actually, this is not even the basic, this is pre-basic buck converter. It converts a DC voltage of 5 volts to another voltage of 2.5 volts, and at least theoretically the power consumed by the DC to DC converter circuit is 0. In practical life, of course, it is never 0, but we'll come to that subsequently. And we saw that the ripple was 2.24 millivolts. It turns out that in real life applications, 24 millivolts is not small enough. So we'll need to reduce it further, but we'll need to reduce it further without increasing the switching frequency. But we'll see that in the next lecture. Let us look at a little more theory of this RL circuit from a different perspective. So what we did just now, what we did was we did a transient analysis of the circuit. Now let us do a sinusoidal steady state analysis of the same circuit and arrive at the same conclusion. So let us think of this circuit with a sinusoidal input voltage. Let us say Vs is a sinusoid of some frequency omega. All right. Then we know that this circuit, an LR circuit with a sinusoidal input voltage, acts as a low pass filter, so that the output is a low pass filter version of the input. And if we derive the transfer function Vo j omega by Vs j omega in sinusoidal steady state, we write RL divided by RL plus j omega L, and we take RL down, so we get 1 plus j omega L by RL. And if we define omega naught as RL by RL, then we can write this as 1 over 1 plus j omega by omega naught. So this is a first order low pass filter with a minus 3 dB frequency of omega naught. All right, we've seen this and done this analysis last semester. Now, suppose Vs is actually a square wave, all right, as we were discussing until this slide. If Vs is a square wave, then what will be the output of this circuit? For a sine wave, it is this. What is fit? This is a square wave. Now a square wave, so let us define this to be our square wave, which I have shifted slightly so that about the zero axis it is an even function. And so let us say it is a square wave that goes from 0 to Vm, and let us say that the voltage is Vm for a time capital T1, and it is the total time period is capital T. Then this is a periodic function of time, and therefore it can be expanded as in a Fourier series, which I assume you have studied, I think last semester. So if we were to expand this in a Fourier series, and because I have made it an even function of time, VST can be written as only cosine term. So we'll say it is A0 plus A1 cos omega naught t plus A2 cos 2 omega naught t plus A3 cos 3 omega naught t, where omega naught is 1 by capital T. So I think there's a little, I did a slight mistake here. Let me go back and correct it. So I should not call this omega naught. I should call this, because this is a different omega naught. So let us call this, what shall we call this? Let us call this omega f, just something, right? So that it is different from the frequency of the oscillation. Alright, so this is omega f and this is omega naught, where omega naught is the frequency of the square wave that we have applied, as opposed to omega f, which is the cut 3 dB frequency of the RL circuit. Alright, so this is a Fourier series expansion of this square wave, and where A0, I am only evaluating A0, A1, A2, A3 I am not evaluating. We will see why in just a minute. A0 is what? You have done this before, so I have just written the expression 1 by capital T, 0 to capital T, Vs of t dt. And so if we you integrate Vs over one time period from here to here, then of course here Vs is 0. So Vs is equal to Vm only over a time of capital T1. So that the integral is Vm times T1, the area under this curve, which is Vm times T1, and then divide by T, and let us call D as the duty cycle, and which is equal to capital T1 by capital T, so that A0 is equal to Vm times capital D, where D is the duty cycle. Alright. Now what we are doing is we are inputting this square wave through a low pass filter, which is this low pass filter, and we want to find the output. So here is the question, not a question, is an observation, that if the filter minus 3 dB frequency, which we've called omega f, is much less than omega naught, alright, the omega naught being this. So if the filter is frequency minus 3 dB frequency is much smaller than omega naught, then all these so this is a component with a frequency omega naught, this is a component with a frequency twice omega naught, thrice omega naught, and so on. So because that is LR circuit is a low pass filter, it will filter out all of these components if omega f is much smaller than omega naught. They will all become very small at the output, and all that will be left at the output is A0. Alright, so at the output, effectively, I'm sorry, this is not Vs, this is Vo. The output is approximately equal to A0. All the other components are filtered out and their magnitudes have become negligibly small, and therefore at the output we get A0, and how much is A0? As we just saw, A0 is Vm into D into Vm. So the output therefore is a DC voltage, because all the AC components have been filtered out. So this is an explanation of our circuit in the frequency domain. In the time domain, we say that we are switching the circuit so fast that the variation in the output voltage becomes very small, because it is not getting sufficient time to change. In the frequency domain, we say that the frequency of the switching frequency is so high compared to the minus 3 dB frequency that all the AC components are filtered out. Alright. Also, the other thing we note here is that the magnitude of the output DC voltage can be varied by varying the duty cycle. Alright, in our earlier SPICE simulations, we kept duty cycle at 0.5 and Vm was 5 volts, and therefore VO was 2.5 volts. But you can change, we can get different output voltages with the same input voltage simply by varying the duty cycle of the square wave that we've applied. Alright, okay, now let us do a little more SPICE simulation in the frequency domain. So we use the same numbers, 10 ohms, 100 microhenry. Now we'll apply an AC signal and see the output of the circuit. So let us see, where is the circuit? This one. Okay, same circuit. Now instead of AC, instead of a transient, we'll apply an AC. Alright, so and we'll do an AC analysis. Let's run this. So now look at the output voltage. Alright, so the output voltage, this is a Bode plot. So we're doing an AC analysis. So we're drawing a Bode plot. So at low frequencies, the output is 0 dB, which is 1 volt. So input is 1 volt. So the output is also 1 volt. The 3 dB frequency is somewhere here, minus 3 dB, which should be about, it is 16 kilohertz, alright, 15.9 kilohertz, I have not, so minus 3.04 dB, 16 kilohertz, and the square wave that we want to apply, we are not applying a square wave here. This is just a Bode plot with a sine wave. But if we were to apply a square wave of a time period 0.02 microsecond, that corresponds to a frequency of 8 megahertz. So on this plot, 8 megahertz is here, roughly here. It's 8. I'm sorry, not even here. It is here. 8 megahertz is here, and at 8 megahertz the output voltage is minus 54 dB. So let's see that in volts. So at 8 megahertz the output voltage is about 2 millivolts. Alright, so the AC component at the output will be about 2 millivolts if the input is 1 volt. So let's make it 5 volts, which is what we had in our transient analysis. So if we make it 5 volts, the same plot, the output is nearly 10 millivolts. So this is the this is the amplitude. So the ripple will be twice of this, about 20 millivolts. Alright, so this is about the same as what we had obtained while doing the transient analysis, as it should be. So again, basically arriving at the same result from a different angle. Alright, okay, so this is our basic DC to DC converter if Vs is a square wave of a high frequency. Alright, so let us conclude this and then we'll pick this up next time. So we say that by rapidly switching the voltage across an RL circuit, or more generally across any low pass filter, right? RL is the basic low pass filter. If we switch this input voltage between two DC voltages, let us say 0 and Vin, the output voltage of the circuit is practically a DC voltage whose magnitude is determined by Vin and the duty cycle of the switching voltage. This is a principle of all buck converters and what are called as boost converters. Buck converters are DC to DC converters whose output voltage is smaller than the input voltage. Boost converters have an output voltage which is larger than the input voltage. Here we will not study boost converters, we will just focus on buck converters, but the circuitry and everything is very, very similar. There are also buck boost converters which can convert the input voltage to smaller or larger output voltages. Alright, so we will stop here And in next lecture we'll talk about actual buck converter circuits. This is just the what we study now is just the basic principle of operation. Next lecture we'll go to the actual circuitry. Okay.